Modern wells require pumps, electricity, and constant maintenance. When power fails, water stops flowing. Medieval wells built with stone, clay, and understanding of groundwater provided reliable water for centuries without any mechanical systems. The water remained clean, the structures stayed intact, and communities survived droughts that would devastate modern infrastructure. This is the story of a hydraulic engineering technology so sophisticated that hydrologists are only now understanding how it works and why every water system you depend on is designed to fail. Chapter 1. The pump that stops. Your home water comes from municipal systems or private wells, both dependent on electric pumps moving water from source to tap. This dependency is absolute when power fails. Water stops flowing within hours as pressure tanks empty. In February 2021, Texas power failures left 12 million people without running water. Homes had intact wells and full aquifers beneath them, but without electricity to run pumps, the water was inaccessible. People resorted to melting snow and collecting rainwater techniques medieval peasants would recognize because modern infrastructure had failed. The average submersible well pump lasts 15 to 25 years before requiring replacement. The pressure tank lasts 10 to 15 years. The electrical controls need replacement every 8 to 12 years. Over 50 years of homeownership, expect to replace the entire well system 2 to 3 times at costs of $3,000, $8,000 per replacement. Total lifetime cost, $10,000, $20,000, plus ongoing electricity consumption of 400 to 800 kilowatt-hours annually. The system works excellently until any component fails. Then you have no water until repairs are made, which might take days or weeks depending on parts availability and contractor schedules. The fragility is engineered into the system through complexity and dependency. Meanwhile, in the village of Mittenwald, Germany, a medieval stone well built in 1372 still provides water. No pump, no electricity, no mechanical systems. Just stone shaft, descending 15 meters to groundwater, with hand-operated rope and bucket. The well has functioned continuously for 652 years, through wars, plagues, climate changes, and technological revolutions. The stone shaft shows minimal deterioration. The water remains clean and drinkable. The system requires no maintenance beyond occasional cleaning of accumulated sediment. Thousands of euros spent across centuries in modern infrastructure terms, essentially free. Medieval engineers built this well expecting it to serve indefinitely. Modern engineers build systems expecting replacement every 15 years. The difference is design philosophy. Build for permanence versus build for planned obsolescence. Chapter 2. The stone that holds water. Medieval well construction began with site selection, finding the location where groundwater was closest to surface and most abundant. This required no instruments, just observation of vegetation patterns, soil moisture, behavior of existing springs, and in some cases, dowsing controversial technique involving forked sticks that somehow identified water locations with surprising accuracy. Once the site was selected, excavation began. Workers dug circular shaft, typically 1.2 to 1.8 meters in diameter, through soil and rock layers until they reached the water table. The digging might extend 5 to 20 meters deep, depending on local geology. This was dangerous. Work collapses, gas pockets, drowning, but communities accepted the risks because water was life. As the shaft descended, it was lined with stone. Not just any stone. Medieval well builders selected specific types based on properties that modern hydrogeology has validated. The stone had to be non-porous enough to prevent contamination from surface water seeping through joints, but permeable enough at the base to allow groundwater inflow. It had to be chemically stable, not dissolving or releasing minerals that would contaminate water. Limestone, granite, and certain sandstones were preferred depending on regional availability. The stones were cut to precise curves, creating circular shaft with joints so tight that mortar was often unnecessary, though lime mortar was typically used to ensure impermeability. The bottom of the well was specially constructed. Rather than solid stone, The base incorporated permeable stone or gravel layers that acted as filter, allowing groundwater to enter while excluding sediment. This filter layer was sophisticated engineering grain size distribution optimized to maximize water flow while preventing fine particles from entering the well. Modern water wells use manufactured sand filters or slotted casings to achieve the same purpose. Medieval wells achieved it through careful selection and placement of natural materials. The top of the well was crucial for preventing contamination. The stone lining extended above ground level, creating raised rim that prevented surface runoff from flowing into the well. Often, the wellhead was covered with wooden or stone roof, protecting from rain, debris, and accidental falls. The entire structure was designed to separate surface water potentially contaminated by human and animal activity from the clean groundwater feeding the well. This separation was critical to public health. Wells that lacked proper construction became contaminated, spreading waterborne diseases. Communities quickly learned which wells stayed clean and which didn't, encoding this knowledge in location and construction standards. Chapter 3. The clay that seals forever. The most critical and least visible part of medieval well construction was the clay seal, a layer of impermeable clay packed around the upper portion of the well shaft, preventing surface water infiltration. This seal began 1 to 2 meters below ground surface and extended to just below surface level, creating barrier that forced surface water to flow away from the well rather than down the shaft exterior. The clay selection was specific. Medieval builders used what modern soil science calls high-plasticity clay material, with high proportion of clay minerals like montmorillonite that swell when wet, creating impermeability. They tested clay by feel and workability, selecting material that was sticky, moldable, and didn't crack when dry. The clay was placed in layers, each compacted thoroughly before the next was added. The compaction removed air voids that could provide pathways for water infiltration. The builders used wooden tampers, stone tools, and sometimes just feet and hands to achieve proper density. This labor-intensive process created seal that would last centuries. As the clay aged in place, it consolidated further under soil weight, becoming progressively more impermeable. Tree roots couldn't penetrate the dense clay. Freeze-thaw cycles at depth were minimal, preventing cracking. The seal improved with age. Modern well construction uses bentonite clay, commercially processed material, that's essentially refined montmorillonite. This works excellently, but requires purchasing manufactured product. Medieval builders achieved the same result by selecting appropriate natural clay from local sources. Research at the Technical University of Denmark analyzed clay seals from medieval wells, measuring their permeability using modern hydrological testing equipment. The 400 to 600-year-old clay seals showed permeability coefficients of 10 to the power of -8 to 10 to the power of -9 meters per second, effectively impermeable. Modern bentonite seals achieve 10 to the power of -8 to 10 to the power of -9 meters per second, identical performance. The medieval construction, done without understanding of soil mechanics or permeability measurement, matched modern engineered standards through empirical methods refined across generations. Chapter 4. The water that purifies itself. Medieval wells consistently provided cleaner water than surface sources. Rivers, ponds, collected rainwater. This wasn't accidental but result of natural filtration occurring as water moved through soil and rock to reach the well. Groundwater begins as rainfall infiltrating soil. As it percolates downward, it passes through various geological layers, soil horizons, weathered rock, fractured bedrock. Each layer acts as filter, removing particles, bacteria, and contaminants. By the time water reaches the aquifer feeding a well 10 to 15 meters deep, it has been filtered through meters of natural material. The filtration is both physical and biological. Physically, soil pores strain out particles larger than the pore-sized bacteria, protozoa. Suspended solids are trapped in the soil matrix. Biologically, microorganisms in the soil metabolize organic contaminants, breaking them down into harmless compounds. The soil acts as living filter, continuously processing water as it flows through. Medieval well builders understood this empirically. They knew that deep wells produced cleaner water than shallow wells. They knew that wells in certain soil types stayed cleaner than wells in other soils. They couldn't explain the mechanisms, but they observed the patterns and built accordingly. Water from wells drawing from confined aquifers, where impermeable layers prevent direct surface contamination, is typically microbiologically safe without treatment. The geological filtration is sufficient to remove pathogens. Water quality analysis from historical wells shows this. The Institut für Wasserforschung in Germany sampled 50 medieval wells still in use, testing for bacteria, nitrates, heavy metals, and other contaminants. Over 80% met current drinking water standards without any treatment. The wells ranged from 300 to 700 years old. The natural filtration they depended on still functioned. Some wells showed elevated nitrates from modern agricultural contamination, but this was recent pollution, not failure of the well itself. Wells in areas without intensive agriculture remained pristine. The contrast with modern municipal water is stark. Surface water treatment requires chlorination, filtration, flocculation, and continuous monitoring. Even after treatment, concerns remain about chlorination byproducts, pharmaceuticals, and emerging contaminants. Groundwater from properly constructed wells requires minimal treatment. Nature does the work. Chapter 5. The depth that defies drought. Medieval communities survived droughts that would devastate modern towns. The secret was well depth accessing groundwater reserves that remained stable even when surface water disappeared. A well reaching 15 to 20 meters typically penetrates below the seasonal water table fluctuation. Surface water streams and ponds respond immediately to rainfall patterns. Weeks without rain, and surface sources dry up. Groundwater responds slowly. Water in deep aquifers represents rainfall from months or years earlier, averaging out seasonal variation. During drought, the water table drops, but deep wells continue producing water long after shallow wells and surface sources fail. Historical records document this. During the medieval warm period, 950 to 1250 CE, Europe experienced significant droughts. Chronicles describe rivers drying, crops failing, and famine, but they rarely mention wells going dry. The communities with properly constructed deep wells had water even when agriculture failed. This wasn't luck, but engineering. Wells were deliberately overbuilt, excavated deeper than necessary during normal rainfall to ensure security during drought. The extra depth was insurance, costly to construct but invaluable during crisis. Modern suburban wells are often drilled to minimum viable depth, just deep enough to meet current water demands. This minimizes drilling costs but eliminates the safety margin. When drought lowers the water table, shallow wells run dry, requiring expensive drilling extensions or new wells. The short-term cost savings creates long-term vulnerability. The aquifer physics are straightforward. Groundwater exists in porous rock layers, saturated with water. The top of this saturated zone is the water table, which rises and falls seasonally. A well penetrating 5 meters below the normal water table has 5 meters of safety margin. Even if drought drops the water table 3 meters, the well continues producing. A well penetrating only 1 meter below normal water table goes dry with minimal drought. Medieval well builders couldn't measure water table depth or calculate safety margins mathematically, but they observed which wells survived droughts and which didn't. They learned that deeper was safer, and they built accordingly. The empirical observation encoded hydrological principles they couldn't articulate. Chapter 6. The hand that never tires. Drawing water by hand, lowering bucket on rope, raising full bucket, emptying into containers, seems like exhausting labor compared to electric pumps. But medieval communities developed tools and techniques that made hand drawing efficient and sustainable. The windlass horizontal cylinder rotated by handle, Winding rope around the cylinder provided mechanical advantage. Instead of lifting the bucket's full weight directly, you rotated the handle, and the windlass multiplied your force. A properly designed windlass with 10-to-1 mechanical advantage reduced a 20-kilogram bucket to feeling like 2 kilograms. The ergonomics were optimized through centuries of use. Handle length, windlass diameter, rope attachment points, all were proportioned to maximize efficiency. Archaeological studies of medieval well equipment show remarkable consistency in dimensions, suggesting standardization based on biomechanical optimization. In community wells serving multiple households, more sophisticated systems developed. The wells sweep a long lever balanced on fulcrum, with bucket attached to one end and counterweight on the other made water drawing nearly effortless. You pull down on the light end, raising the heavy water-filled bucket on the opposite end. The counterweight assisted the lift. Some wells used tread wheels, large wheels that people or animals walked inside, like hamster wheels, providing continuous rotary power. One person walking steadily could raise water from considerable depth indefinitely. The Almuñécar well in Spain, built in 1000 CE, used this system to lift water 40 meters from underground aquifer. These human-powered systems required no fuel, no electricity, no complex maintenance. They worked during wars, plagues, famines, any crisis. As long as humans remained to operate them, water flowed. Modern electric systems stop the moment power fails, rendering the entire well system useless until electrical supply is restored. The human-powered systems were slower. Drawing water took 5 to 10 minutes per household daily versus seconds turning on a tap. But this time, investment was reliable and independent. You couldn't lose your water supply because of power grid failure or equipment breakdown beyond your ability to repair. Chapter 7. The community that shares water. Medieval wells were often communal, serving multiple households or entire villages. This created social infrastructure around water, with rules governing access, maintenance responsibilities, and conflict resolution. The communal well required collective maintenance. The stone shaft needed occasional cleaning to remove accumulated sediment. The rope and bucket needed replacement as they wore. The wellhead structure needed repairs. These tasks were divided among households using the well, creating shared labor obligations. This collective responsibility had advantages. The maintenance burden on any single household was minimal, perhaps a few hours per year, but the aggregated labor kept the well functioning optimally. No household could neglect maintenance and free ride on others' efforts. Social pressure ensured participation. The communal system also created resilience. If one household fell on hard times, illness, crop failure, death of working-age members, other households temporarily covered their maintenance obligations. The community supported itself through informal reciprocity. Modern private wells eliminate this collective structure. Each household maintains its own system, bearing full cost and responsibility. This provides autonomy but eliminates mutual support. When your well fails, your problem is yours alone. There's no community obligation to assist. The water became commodity rather than commons. The historical shift from communal to private water systems parallels broader changes in resource management, from collective stewardship to individual ownership, from shared responsibility to isolated dependence. Whether this shift represents progress or loss is debatable. Communal systems required social cooperation and subjected individuals to collective norms. Private systems provide freedom but eliminate mutual aid. The medieval model created interdependence. The modern model creates independence and isolation. Chapter 8. The failure that teaches. Not all medieval wells succeeded. Some were dug in wrong locations, finding insufficient water or none at all. Some were poorly constructed, with inadequate stone lining collapsing or clay seals failing. Some became contaminated, spreading disease. These failures provided harsh lessons that refined well-building knowledge. Contaminated wells were particularly instructive. Medieval people didn't understand microbiology, but they observed that some wells made people sick while others didn't. They noticed that wells downhill from latrines or cemeteries were more likely to cause illness. They saw that wells with damaged clay seals became fouler after rains. These observations, accumulated across communities and generations, created empirical rules. Don't build wells near waste disposal areas. Maintain proper distance from potential contamination sources. Protect wellheads from surface runoff. Ensure clay seals remain intact. These rules encoded public health principles discovered through tragedy and observation. Modern well regulations set back distances from septic systems. Sanitary seals, approved construction methods formalize knowledge that medieval communities developed informally. The regulations aren't arbitrary bureaucracy, but codified lessons from centuries of trial and error. Some failed wells were abandoned, their locations remembered as places to avoid. The landscape accumulated knowledge. This spot has good water. That spot has bad water. This depth is sufficient. That construction method works. The information wasn't written down, but was embedded in practice and transmitted through apprenticeship and community memory. When these oral transmission systems broke down through population disruption, cultural discontinuity, or dismissal of traditional knowledge as superstition, the accumulated wisdom was lost. Modern drilling sometimes repeats medieval mistakes because the historical knowledge wasn't preserved in forms modern engineers recognize. Chapter 9. The economics of permanent infrastructure. Building a medieval stone well required significant upfront investment, perhaps several months of community labor or substantial payment to specialized well diggers. For poor communities, this represented enormous expense. But once built, the well required minimal ongoing cost. Maintenance was occasional and mostly labor, not materials. The well functioned for centuries without major investment. Calculating the economics. A well costing 1,000 hours of labor to construct and requiring 10 hours annually for maintenance provides 500 years of service at 6,000 total labor hours, or 12 hours per year averaged across its lifetime. Compare this to modern drilled well, costing $10,000 to install, requiring $500 annually in electricity and maintenance, and needing full replacement every 25 years. Over 500 years, this totals $200,000 in installation costs, plus $250,000 in operating costs, $450,000 total. The medieval well's labor, even valued at modern wages, costs perhaps $100,000 total. The difference is order of magnitude. The medieval approach optimized for low ongoing costs through high initial durability. The modern approach minimizes initial cost while accepting high ongoing costs and frequent replacement. For institutions thinking across centuries, churches, monasteries, villages, the medieval approach was economically rational. For individuals thinking across years, modern homeowners, businesses, the modern approach seems rational because the time frame is truncated. If you expect to sell your house in 10 years, you don't care if the well fails in 25 years, that's the next owner's problem. If your community expects to exist for centuries, you care deeply about long-term costs. The economic rationality depends entirely on the time frame considered. Modern economic systems discount future costs heavily. A cost 25 years away is valued at perhaps 30% of present cost in net present value calculations. This discounting makes planned obsolescence appear economically efficient. Medieval economic systems didn't discount future costs as heavily, partly from different financial theory, partly from stronger intergenerational obligations. This made permanent infrastructure economically attractive. Chapter 10. The Master Who Dig. In Brittany, France, a traditional well digger named Jean-Claude Moreau maintains a nearly extinct craft. He's 71, learned well digging from his father, who learned from his father. He's one of perhaps 20 people in Europe still hand-digging stone-lined wells using medieval techniques. Jean-Claude explains the process. It begins with finding water he uses, dowsing, acknowledging that scientists dismiss it but insisting it works through mechanisms he doesn't understand. The forked hazel branch twitches downward at specific locations, indicating water presence. He's dug hundreds of wells, and the method succeeds far more than random chance would predict. The excavation proceeds carefully. 2 workers in the shaft dig and load earth into buckets, which a surface crew hauls up. As depth increases, a windlass aids lifting. The diggers watch constantly for dangerous conditions, unstable soil, groundwater seepage that could cause collapse, bad air accumulating at depth. Every meter requires hours of work. The stone lining follows excavation closely, never leaving more than a meter of unlined shaft. Jean-Claude or his assistant cut stone to fit the curve, creating interlocking pattern that's structurally self-supporting. No mortar is used until the shaft is complete. Then lime mortar is pointed between stones from inside. The clay seal is placed from outside, excavating around the completed shaft's upper portion and packing selected clay in layers. This is especially difficult, requiring precise judgment of clay quality and moisture content. Too wet, and it won't compact properly. Too dry, and it won't seal. Jean-Claude has dug 47 wells in his career. He's training no one. His son became an engineer, his daughter a teacher, neither interested in hand-digging wells. When Jean-Claude retires or dies, his knowledge dies with him. The craft will survive perhaps in historical reconstruction or rare preservation projects, but as living trade serving practical needs, it's effectively extinct. He charges €15,000, $25,000 for a complete well, taking 3 to 6 weeks depending on depth and conditions. Modern drilled wells cost €8,000, $12,000, completed in 1 to 2 days. Clients choosing Jean-Claude do so for specific reasons. Aesthetic desires for traditional construction, locations where drilling equipment can't access, or philosophical commitment to traditional methods. The market is tiny, perhaps 1 or 2 commissions per year. He supplements income with stone masonry and consulting on historical well restoration. Chapter 11. The Science that Explains Tradition. Modern hydrogeology has extensively studied historical wells, validating traditional construction methods while revealing underlying principles. Research programs at universities worldwide analyze well design, water quality, aquifer characteristics, and long-term performance. The findings consistently show that well-constructed medieval wells were sophisticated hydrological engineering. Studies at Delft University of Technology in Netherlands used computational fluid dynamics to model water flow around historical wells. Their simulations revealed that the well's dimensions, diameter, depth, permeable base design, were optimized for maximum sustainable yield. Drawing water too rapidly drops the water level inside the well faster than groundwater can replenish it. The well temporarily runs dry, even though the aquifer contains abundant water. Proper well design matches storage capacity to recharge rate, allowing continuous moderate use without depletion. Medieval wells achieved this through empirical optimization. Builders observed that certain dimensions worked better than others, and they standardized on proportions that modern modeling confirms are near optimal. Chemical analysis of water from historical wells shows interesting patterns. Wells in limestone regions often have slightly alkaline pH and elevated calcium characteristics of limestone aquifers that buffer acidity and provide beneficial minerals. Wells in granite regions have lower mineral content but are more corrosion-resistant for metal tools. The well water's chemistry reflected local geology, and communities adapted their usage accordingly. Limestone water was preferred for drinking. Granite water was better for washing. Microbiological studies found that deep wells maintained stable microbial communities, not sterile, but dominated by harmless groundwater bacteria that outcompeted pathogens. This protective biofilm actually enhanced water quality by preventing pathogenic colonization. Modern disinfection treatments that kill all bacteria eliminate this protection, sometimes making wells more vulnerable to contamination. The research validates that medieval well construction was empirically derived engineering, achieving results that modern theoretical approaches struggle to improve upon. The builders couldn't explain why their methods worked, but centuries of observation had optimized the design. Chapter 12. The contamination that modern life creates. Medieval wells faced contamination risks from human and animal waste, cemeteries, tanneries, and other pre-industrial pollution sources. Medieval builders learned to separate wells from these sources through distance and placement. Modern pollution is different. Agricultural chemicals, industrial solvents, pharmaceuticals, microplastics, contaminants that medieval builders never encountered, and current well construction wasn't designed to address. Nitrogen from agricultural fertilizers is particularly problematic. It's highly mobile in groundwater, traveling considerable distances from application sites. Many rural wells now show elevated nitrates, creating health risks, especially for infants. The contamination comes from farming practices adopted in the 20th century, intensive fertilization that medieval agriculture never used. The wells haven't failed, the environment has changed. Pesticides and herbicides present similar challenges. These compounds can persist in groundwater for years, migrating slowly through aquifers. Wells that provided clean water for centuries now require treatment or abandonment because agricultural chemicals have reached the aquifer. Industrial solvents, particularly chlorinated compounds used in manufacturing and dry cleaning, are dense, mobile, and persistent. They've created widespread groundwater contamination in industrial areas. Historical wells in these regions often show solvent contamination from sources that closed decades ago. The contamination persists because the compounds degrade extremely slowly in groundwater. The fundamental problem is that groundwater remediation is extraordinarily difficult and expensive. Surface water contamination can be addressed by stopping pollution inputs and waiting for flowing water to carry contamination away. Groundwater moves slowly, perhaps meters per year, meaning contamination persists for decades or centuries. Once an aquifer is polluted, it's effectively lost for multiple generations. Medieval communities polluted groundwater too. Archaeology shows contamination around medieval tanneries and blacksmiths, but the pollutants were mostly organic compounds that degraded naturally over decades. Modern synthetic chemicals don't degrade, they accumulate indefinitely. We've created pollution that our descendants 500 years from now will still be dealing with. Chapter 13. The regulation that tried to help. Modern well regulations attempt to ensure water safety through standardized construction requirements. Minimum depth, setback distances from contamination sources, approved materials, sanitary seals, well caps, testing requirements. These regulations embody lessons from centuries of experience, plus modern understanding of hydrology and microbiology. But regulations written for drilled wells with pumps don't easily accommodate traditional hand-dug stone wells. The construction methods are different. The materials aren't standardized. The designs don't match regulatory templates. This creates barriers. Someone wanting to construct a traditional stone well for historical accuracy, aesthetic preference, or philosophical reasons faces regulatory obstacles. The well might not be approved construction, even if it would function perfectly. The permitting process may require engineering plans that traditional builders don't have. Inspectors may not know how to evaluate stone well construction because their training covers only modern drilled wells. Some jurisdictions simply prohibit hand-dug wells as inherently unsafe, regardless of construction quality. These blanket bans eliminate traditional methods without evaluating whether they achieve regulatory goals. A properly built stone well can meet water quality and safety standards, but it does so through different means than regulations specify. The regulations assume specific technology drilling, pumps, casings, and prohibit alternatives. This is regulatory rigidity, not safety. Reform would require performance-based standards. Specify the outcomes required: water quality, contamination protection, while allowing flexibility in construction methods. This would accommodate traditional techniques while maintaining safety. Some European countries have adopted this approach. Sweden and Germany have regulations allowing traditional wells if they meet water quality standards and incorporate appropriate sanitary protection. But most jurisdictions apply one-size-fits-all rules that effectively prohibit traditional construction. Chapter 14. The revival that's emerging. A small but growing movement is rediscovering traditional well construction, not as historical curiosity, but as practical alternative to drilled wells. The motivations are diverse: desire for grid-independent water systems, aesthetic preferences for stone construction, environmental concerns about drilling impacts, and resilience, thinking that values low-technology solutions. Homesteaders and off-grid communities are particularly interested. A hand-dug well requires no electrical infrastructure, no specialized equipment beyond local availability, and no ongoing energy inputs. For remote properties without grid access, traditional wells are often more practical than drilled wells, requiring electricity or generators. Natural builders constructing homes from traditional materials often include traditional wells as complementary systems. Stone well construction fits philosophically and aesthetically, with cob walls, lime plaster, and thatched roofs. The building system as a whole embodies low-technology, durable, locally sourced construction. Some permaculture practitioners incorporate traditional wells into integrated water systems, combining rainwater, harvesting, ponds, swales, and deep wells to create resilient multi-source water supplies. The deep well provides backup during drought when other sources fail. Challenges remain. Finding practitioners who know traditional well construction is difficult. Perhaps 50 to 100 people worldwide have serious expertise. Regulatory approval can be problematic. Costs are higher than standard drilled wells in the short term, though the life cycle costs favor traditional construction. And convincing skeptical neighbors and officials that hand-dug stone wells are legitimate rather than foolish primitivity requires patience and education. Despite challenges, the revival is real. Workshops teaching traditional well construction are appearing. Online communities share information, troubleshoot problems, document successes. The knowledge is slowly expanding from near extinction to viable niche practice. Whether this remains tiny movement or grows into significant alternative to standard well drilling depends on broader cultural shifts. Whether low-technology resilience gains acceptance, whether environmental and grid concerns drive off-grid living, whether economic factors make long-term durability attractive versus short-term cost minimization. Chapter 15. The water that waits. You probably cannot build a traditional stone well. The regulatory barriers are substantial, the expertise is rare, the labor requirement is significant, but the lesson the well teaches applies regardless of whether you build one. That lesson is, infrastructure optimized for durability serves better than infrastructure optimized for convenience. If you think across generations, rather than years, your municipal water or private drilled well works excellently until it doesn't. Then you're entirely dependent on repair systems beyond your control. Utility companies, well contractors, equipment suppliers, electricity grids. The fragility is hidden during normal operation but becomes obvious during crisis. A medieval community with stone well had water regardless of external systems. Plague killed everyone, the well remained. War destroyed the village, the well remained. Economic collapse eliminated trade, the well remained. The water was guaranteed, as long as someone could lower a bucket. This isn't nostalgia for medieval life, which was harsh in countless ways. It's recognition that certain fundamental design principles create resilience that modern systems lack. Permanence over obsolescence, simplicity over complexity, local over distant, controllable over dependent. These principles apply far beyond wells to food systems, energy systems, building materials, tools. The medieval well is just one example of technology that's inferior by modern convenience standards, but superior by resilience standards. The water that never runs dry is still there in aquifers beneath our feet, in stone-lined shafts that preceded our grandparents', in techniques practiced for millennia before drilled wells existed. It's waiting, patient as groundwater, ready to teach that the most reliable technology isn't always the most advanced, and sometimes the solutions that served for centuries can serve again when modern systems fail. The well is permanent. The question is whether we're wise enough to remember why permanence matters before the next crisis reveals what we've lost.